Welcome back. This is part 2 of the Unit 6 Nuclear Chemistry Review Worksheet or Study Guide. Yesterday we left off on number 21, so we'll start there. On 21, we see a skeleton has been found in the woods. Oh my gosh. And the police would like to place the approximate time of death. Okay. A sample of bone from the skeleton produces 12.0 disintegrations per minute, bone of recent origin produces 14.0 disintegrations per minute. Calculate the age of the bone sample, okay, and then they tell us the half-life of carbon. Okay, so we know our half-life is 5,730 years. Okay, so we know we're going to need K. Let's go ahead and solve for K. That's the first thing I do anytime I see a half-life given to me is I just go ahead and do that. Okay, and so I get a K equal to 1.2094. I left some decimals there, times 10 to the negative 4. Okay, and then our unit is year to the negative 1. Okay, and then in the problem, we're given information that refers to activities, not mass or mole. And so I want to use my form of the equation that is natural log is the activity over the initial activity equal to negative K times T. I'm solving for time because they want to know the age of that bone sample. And then they tell us that our A sub 0 is, which one of those? Sometimes that's the trickiest part, right? Is just figure out which one's your A, which one's your A sub 0.
14.
Yeah, our initial one is the 14. Remember, the bottom one is going to be the biggest, so that's another kind of clue or indicator. Okay, so if our bottom one is the 14, our top one must be the 12. That's disintegrations per minute. Okay, equals negative. Running out of room. We have our K. Fix that real quick. Okay, we have 1.2094 times 10 to the negative 4. Sorry. Year to the negative 1 times T. Solving for T. Oh, that looked like a smiley face. Did you see that? For just a second. Okay. So now what I'm going to do on the left side is I'm going to enter that into my calculator exactly the way I see it. So natural log, parentheses, 12 divided by 14, close parentheses. And I get negative 0.15415 for this side. Okay, equaling, I'm going to go ahead and rewrite that again, even though I know I don't have room. Equaling our negative 1.2094 times 10 to the negative 4 times T. So how do we get rid of that K with our T there? Yeah, we'll divide both sides by that. And so we should get a time equal to 1.27 times 10 to the 3rd years. Okay, so that's the age of that bone. Questions about that one at all? Okay, on our number 22, it says the half-life of the decay of uranium-238 to lead-206 is 4.5 times 10 to the 9 years. A mineral sample contains 50 milligrams of uranium-238 and 14.0 milligrams of lead-206. What is the age of the mineral? And so we have our half-life equal to 4.5 times 10 to the 9 years. Let's go ahead and get K. So I have a K constant, a decay constant of 1.54 times 10 to the negative 10. here to the minus 1. Okay, we are solving for time, we know that. Okay, and we're given milligrams of uranium and lead. Well, what we need to realize on that, or realize about that, is that lead used to be what? It used to be uranium, right? And so as the uranium decayed through that amount of time, it became that lead. So what we're going to need to do is use the 50 as our N, okay, because that's how much uranium we have now. And then we're going to have to convert that 14 milligrams of lead that we have now to how much uranium that would be, okay? And so the way we do that, that'll be our N sub 0 once we add it to our current amount of uranium. So we're going to start with that 14.0 milligrams. We have lead, 206 over 1. And then all we have to do there is use our mass numbers as a ratio. And so the lead will get the 206. We need the one for uranium on top. Okay, and so we get 16.17, I put probably too many decimals there, 1748 milligrams of our 238 uranium. Okay, so that's just the amount that the lead used to be before the decaying process. So now to get our N sub 0, we need to add that to how much uranium we still have. So we're going to add our 50 to that. And so I get an N sub 0 equal to 66.175. Yeah, fix that little error there. 66.175, and that's milligrams of 238 uranium. Okay, so now since we're given information about mass, we're going to use our Ln parentheses N over N sub 0 equals negative KT as our equation. Okay, let's have our natural log of N. N is going to be how much uranium we have now, which is the 50.0 milligrams, over our initial amount, which is our total down here, the 66.175, equals our negative K, so 1.54 times 10 to the negative 10, year to the minus 1, and we are still solving for time on this one. Okay, so we have our T. I'm going to enter in natural log of 50 divided by 66.175. I'm going to go ahead and divide by that negative 1.54 times 10 to the negative 10, and I get a time equal to 1.8 times 10 to the 9 years. Pretty old, okay, but that's the age of that mineral. Questions on that? Bless you. Okay, let's look at our AP free response questions. Okay, so our first one, we're going to answer each of the following questions regarding radioactivity. So for part A, it says write the nuclear equation for the decay of plutonium-234 by alpha emission. Okay, so we're going to start with our isotope here, our 234. Pu is our atomic, or our chemical symbol. Atomic number is a 94. And we are undergoing alpha emissions. We want to show that with our helium nucleus. I'm going to write that first this time. And so to figure out our daughter nuclide, remember we need our top numbers to match, our bottom numbers to match. And so I know my top number for my daughter nuclide must be 230. And my atomic number then for my daughter nuclide must be a 92, which corresponds with the element uranium. So that would be your balanced nuclear equation for that one. Okay, for part B, it says account for the fact that the total mass of the products of the reaction in part A is slightly less than that of the original. Okay, so how can we describe that or account for that? What can we say about that? What happened to the mass? Because we know when we have our daughter nuclide, it weighs less than the protons and neutrons we started with, right? What happened to that mass? It was converted to energy. That's where all that energy comes from in these nuclear reactions, exactly. Okay, so let's write, this is my answer. I have the missing amount of mass, which we've been calling the mass defect, right? Mass deficiency. May as well use those terms when we can. Was converted into energy. I got ahead of myself, hang on. Was converted to energy. And I went ahead and explained according to, and I put our E equals mc squared there, because we know that that mass defect times the speed of light squared is equal to the binding energy, and it's related to that. So I went ahead and added that. Okay, for part C, we are going to use this diagram. We're going to draw on it, and we're going to illustrate where our alpha, beta, and gamma rays would go if they're being emitted from this radioactive source here, this box. Okay, and so how would let's start with gamma. If we have a gamma ray emitted from this box in this direction, where's it going to continue to go? Is it going to go towards a positive source, a negative source, or keep on going? It's going to keep on going. Why? Yeah, it doesn't have a charge. It also doesn't have mass or anything, right? It's just a wave of energy being emitted, right? It's not really a particle. So to illustrate that, I'm just going to draw a line. Okay, I'm going to label that with a gamma particle, my symbol. And then it wants us to also explain, okay, describe. So what I put on there is a gamma ray. Is not a charged particle. It is a wave of energy. You can add that. Okay, good. So we've got our gamma ray sorted out. Let's look at alpha. If an alpha particle is emitted from this source in this direction with my arrow here, where's it going to go? Think about the charge. What's the charge on an alpha particle? Positive. Okay, so what is a positively charged thing going to do? It's going to be attracted to the negative side of that electric field. Exactly. So we're going to be alpha particle now. We're going to go towards the negative side. Okay, so let's go ahead and label that alpha. Or we can label it with a helium nucleus. Okay, and so on my explanation there, I put alpha particles are positively charged. They will move towards a negatively charged electric field. So there's our alpha. Okay, so now when we describe that beta particle, when it's emitted from that source, a beta particle is like an electron, right? It's negatively charged, so it's going to go towards the positive side of that electric field. Okay, so we can label it beta or an electron. Okay, so beta particles are negatively charged. And will move towards a positively charged side of the electric field. Okay. Questions on that? Question very similar to that on your test. Okay. Very typical kind of question on the AP free response too for the short answers. Okay. This is our last one. Part D, why is it not possible to eliminate the hazard of nuclear waste by the process of incineration? So why can't we just light it on fire and get rid of it? Okay. This is a really interesting question. I like this one. What kind of change is burning something? It's a chemical change. Okay. What does it affect in terms of what part of the atom is affected during a chemical change? Say it again. The electron cloud is affected, right? We have that exchange of electrons, right? So the electron cloud is affected during a chemical change like burning, right? What kind of process is our nuclear radiation? Where is that occurring? That's occurring, yeah, it involves our protons and neutrons, right, which are in our nucleus. Okay, so if we just burn nuclear waste, it's not going to stop the radiation. Now we're just going to have all this radioactive smoke, right? And that's bad. Okay, so burning. Burning would result in a chemical change. Which affects the electron cloud, or the electrons, right? I went ahead and just put not the nucleus. Which is where radioactive decay occurs. Okay, and so if we burn the nucleus, if we burn the nuclear waste, would result in radioactive smoke. Okay, any questions about what we did today or anything from yesterday on the study guide or anything? Okay, thank you all for joining me. Don't forget to like, comment, and subscribe.